All right. So today we're going to do electricity. We started this last week, right? We started looking at electricity and we did an exercise, but we didn't get to finish because of our tests. So now we will go ahead and try and finish it this week. All right, so essentially we want to formulate a simple working definition for the, the term electric current. We want to classify materials or substances as insulators and conductors of electricity, which we did last week. We want to construct simple circuits using lamps, insulated wires, dry cell switches to distinguish between series and parallel surface circuits. You need to draw diagrams to represent series and parallel circuits and conduct investigation with. So this would be if we were at school, but no, we are online. So we're going to see how much we can complete these. All right, so let's continue. All right, so electricity can produce light, heat, and sound when flowing through a circuit. All right, so all circuits, right, they have current inside of them, right, and they have electricity flowing, right, but it depends on the nature of the circuit and the build of the circuit that would decide the output. All right, so a TV would produce both light and sound because of the build of the circuit. That's what we want to try and get here. On the other hand, let's look on a radio. A radio would just produce sound when electricity pass through it, and look on the fridge versus an oven. Whenever we have our oven or a toaster, we would have the heating element of the wires having electricity flowing through them that would cause heat, right, in comparison to a fridge, right? Whenever we have electricity passing through a fridge, it gets colder. So it depends on the nature of the circuit, but essentially everything that has electric current passing through it, that would give it a different function and of course a different output. Now, electricity flows in a closed path to form a circuit and stops whenever the circuit is broken. So if there's a broken circuit, right? Let me see this here. One second. If there's a broken circuit, electricity will not flow. All right. If there's a broken circuit, there will be no flow of electricity or electric current. So we see a closed circuit here. Over here, this is a closed circuit, right? And electricity can flow and the light bulb shines, right? What about this one? Would this be a would electricity flow in this particular circuit here? All right, so electricity would not flow in that circuit, right? Because it is open, right? Now, what if we go ahead and connect this to this particular area here, right? Electricity would now flow now, right? All right, so electricity would now go ahead
Yes,
and
sir.
exactly. All right, so now we have conductors as copper, aluminum, and steel. All right, copper, aluminum, and steel. Um, Let me just send the student the code for the class. Give me a second here. Right, so we have copper, aluminum, and steel. These are the most common conductors that we use for electricity flow. For example, if you want to get electricity from the power plant to your houses, you would find out that copper, aluminum, more than likely you'd use copper wires because it is the most efficient wire. But you would find these inside of the wires that flow that carry essentially carry current. And we have insulators over here. Insulators as rubbers, plastics, glass, wood, and cloth. All right, these are all insulators. And if you realize the electric wires, right, electric wires, they are covered in what exactly? What is that material covers those wires? Or what is on the outside of the wires?
What is on the outside of the wires?
Rubber.
Right. So you would have rubber.
Right.
Rubber,
So
sir.
you would have rubber.
Rubber, sir.
Exactly. Exactly. So you would have a rubber
Exactly.
on
So
the
you would have
outside.
rubber on the outside.
I'm hearing some feedback.
I'm hearing some feedback.
All right. Okay, good. Yeah, so you'd have rubber on the outside of your wires, right? And on the inside, you would have either copper, aluminum, and steel. So we see the various uses of insulators and conductors. And why exactly is rubber on the outside of those wires? Why do we see rubber and not the actual wires carrying current?
Sir, because the cup, whether it be copper or whatever that's inside, so it can damage.
Exactly. Exactly. So if we are exposed to if we are exposed to the electricity, right? Miss Free, I'm going to ask you to close the mic for a second. I'm hearing some noise in the background. All right, so if we are exposed to the electricity, the raw electricity from these wires, then that would cause us to get electrocuted, right? And we wouldn't want that. So therefore, we use insulators as a means of protection from electricity or from the flow of electricity. All right, so we did an activity like this last week, but let's just do a couple more, right? Just to cement this content. Now, I wanted to state whether it is a insulator or conductor. All right, so let's look on the first one. So the first one as a coin or a penny. What exactly is this?
Insulator, sir. An insulator.
All right, so the penny or the coin is an insulator.
Sir.
Yes. Sir, what was the option again?
Is it an insulator or conductor?
Insulator or conductor. So it's an insulator.
No, it's not an insulator, right?
It's an
There's
insulator.
a conductor.
It's a conductor, right? The penny here is made of metal.
How is it a conductor?
Because it's copper, Jordan. It's a type of metal.
All right, so metals are usually
Like
conductors of
iron.
electricity, right? All right. And paper is a conductor or insulator.
Insulator.
All right, and let's look on
Insulator, sir.
exactly, and let's look on our cork here.
Fork is an conductor. Sir.
Cork opener.
Cork. Oh, I think you said fork.
Sorry, this cork opener here.
Conductor.
All right, so there are some sections as a conductor, right? This section would be a conductor or insulator.
Conductor.
Right, this section would be a conductor. And what about the other section?
It will be an insulator.
Insulator.
And then this section would be a insulator. Right, and we have gloves here. What are the gloves?
Conductors.
Are we sure about that?
No, insulators.
Insulator, Amina.
Exactly, so these are insulators. And why do you think these
Sir,
are insulators?
may I ask?
Because it's clothing material.
All right, so I think Jordan has a question.
Sir, I think that was Amelia that answered my question. I was asking what's the difference between the conductor and an insulator.
Yeah, that's what we're going to know. We're going to that next. All right, this is the next slide. All right. but we're just going through this activity first. All right,
Okay.
so these are insulators, right? Why do you think these are made of rubber or wool? Why do you think?
Why I think they're made of rubber or wool?
Yeah.
Sir, because they don't use electricity or need electricity or something like that.
Yeah, so they don't conduct electricity, so therefore we can use them for what?
Protecting.
All right, so for protection, whenever we're dealing with wires, right, or electricity, right?
Yes, sir.
Yeah, if we have on our gloves, then we won't get affected by electricity. So that is one good benefit of
Sir, but that depends on the type of gloves.
right. That depends on the type of gloves, but most gloves they use wool or cloth or either rubber, right? And all of these are insulators. They don't conduct electricity. All right. We can use these four last ones over here. Our set right here are these conductors
Conductors.
all right, so we see that let's say that this is a metal spoon. It would be a conductor or insulator.
Conductor.
All right, and what
A
about our plate?
conductor, sir. A conductor.
All right, so it can what if it's a plastic plate, or let's say it's a glass plate?
Then
Insulator.
Exactly. So it will be an insulator. What about our frying pan here?
Conductor.
All right, so where the food goes, that would be conductor. And what about our rubber? Rubber tire. So our tire would be a conductor as well. Sorry. And then our thermos, what would this be?
Conductor.
Are we sure? What is the thermos?
Sir, I would say insulator.
All right,
because it's kind of plastic.
All right, so
I'd
the thermos.
say conductor because it could be either, sir, depending on the material that they use.
Exactly. So the thermos is essentially
Sir, I said insulator because.
Go ahead.
Look like metal.
Don't worry, sir. Don't worry. Go ahead.
Sir, I would say insulator because that look like metal. Conductor, sorry, because that look like metal.
I'm saying conductor.
All right, so it can either be you have some sections of it as conductors and you have some sections as insulators. Essentially, the thermos is used to keep cold things cold and hot things hot, right? So if it is used to keep hot things hot, it would essentially limit the transfer of heat. So therefore, you have some sections of it as insulators. All right, but on the outside, you usually have a shiny metal that is used to reflect any form of energy. For example, light energy, if you want to keep something cold inside, you would have it shiny on the outside to stop that form of energy and to keep the things inside of it at the particular temperature. All right, so move on to insulators, and we said to insulate energy means to prevent transfer of energy. So it does not allow heat or electricity to pass. All right, we're doing electricity as a topic, but we would generalize for heat and electricity. All right, so you're essentially stopping heat or electricity from transferring when you use our insulators. All right, so rubber, as you said earlier, is essentially used to insulate energy to stop the energy from flowing. On the other hand, conductors, to conduct means that you transfer energy, right? So you allow heat or electricity to pass from object to another object. So some examples of conductors would be metal wires. They are used to conduct electricity, right? Metal pot, of course, is used to conduct heat, right? It would not be smart if you used an insulator as a pot, because you wouldn't be able to transfer heat, right? So we use metals to conduct heat. So are insulators and conductors clear so far?
Yes, sir.
All right, good. All right, so now move on to electric current, right? So we'll do a short exercise now. Let me bring it up. On electric current, that's what we'll focus on mostly for the rest of today and tomorrow. Let me go ahead and bring it up.
Sir, are we going to get all of these on our exam?
Yeah, so you get up to electricity for the exam. Here another question?
Excuse me, sir. Sir. Sir, can you give us a brief explanation of what's going to be on the whole exam, please?
Yeah, that will be done next week. All right.
It will be posted.
All right, so I will talk about the exam, mostly revision for next week. We'll have time on next week to do it, all right?
Okay, thank you.
All right, well, most of the questions, they are from the first and the second test. All right, so it's the same. Some of them are the same structures. I changed up some of the questions, right? But essentially, because this is just one lecture, right? This is just electricity alone, so I can't really get much questions from electricity from this, right? So I would have to go back for some of the questions or repeat some of the concepts from electricity, but it essentially is the same thing. Let me bring this up. Go ahead and share. All right, let's wait until it's coming up now. I don't know why it's taking so long. All right, so here we go. Right. So essentially, this is not showing the entire thing. Why is it not showing the entire thing? All right. All right, so we have a battery here and we have a resistor here. Are you seeing this?
Yes, sir.
All right, so we have a battery here and we have a resistor here. Now, there should be another wire coming around. Maybe I shouldn't use this one. Let me see. Yeah, it doesn't matter. All right, we'll just get this out of the way. All right, so if we use this right here. Do you remember what is used to measure amps or the electric flow, electric current? Do you remember? All right.
No, sir.
All right, no problem. We'll go over it again. But essentially, this is used to measure.
Sir, is it? Sir, is it volt?
No. Right, a meter in amps that is used to measure current. But we'll talk about it again. But we just want to get this out of the way for now. Then we'll pause. So this is the last thing we'll do for now, and then after lunch we'll meet again. All right, so when we increase the power coming out of our battery, look on the speed of our particles. When you increase the power coming out, what happens to the speed of the particles? It increases or decreases?
They increase. They move faster, sir.
So exactly, they move faster.
Increases.
I hear a question.
Is it an ampere meter?
All right, so you're close. It's an ammeter.
What?
All right.
Oh.
Yeah, ammeter. You're close. All right. So if you realize when you increase the voltage on our coming out of a battery, we see that there's an increase in the current or the flow of charge. All right. So you realize that the flow of charge is much more vigorous. If you look on our resistor here, this is called a resistor. It can represent anything. It can represent your fridge, your TV, a light bulb. We usually use the image to represent a light bulb. But if you realize the particles are moving much quicker, and what happens to the temperature when we change it? If say we increase the temperature, what happens to the temperature if we increase the voltage? Look on this meter down here.
Temperature will
So
rise.
it gets hotter.
Exactly, we get hotter. Now look on our meter over here. This is at approximately, let me see, this is about 10, right? This is at about 10. So this is 0, and this is 50, right? This is about 10, right?
Mm-hmm. Yes.
So this is 10, 20, 30,
Yes,
40, 50. What happens when we increase the voltage again?
It gets hotter.
Closer
So
to
it gets
50.
hotter, but what happens? It gets closer to 50, right?
Yes, sir.
Yeah.
So it goes up now
Yes,
to
sir.
about 20. All right, that's what we really want to get from this. So are we understanding this? Anyone not clear what is happening?
Yes, sir, I understand. But sir, what are the green particles?
All right, so the green particles are a part of our resistor. All right, so they can represent anything. It can represent our light bulb. It can represent the particles in a fridge, right? So it's essentially represents the particles in the circuit, or the particles inside the actual material.
Excuse me, sir.
All right, question?
So basically, what is happening on the screen right now is that it's showing how energy leaves the battery.
Right, and it's also showing our flow of charge. So we look on the increase in power coming out of the battery, or the increase in voltage coming out of the battery, and then we observe the flow of charge, or how quickly, or the increase in the speed of the flow of charge or electric current.
Sir, the voltage represents how hot or how cold.
No, the voltage that represents how much power is coming out of the battery. All right, so a current represents how quickly the electrons are flowing, right? These blue things, they are called electrons, and these are the ones that are carrying the electricity. All right, these are the ones that causes the electricity to flow. So the movement of electrons causes that. Now the voltage on the battery, that would, if you increase the voltage, that would cause our electrons to move much faster. So it basically represents the pressure that the battery puts on the system to push the electrons. So we don't want to get too deep inside of it, right? But we just want to say that the voltage is the one that really produces that pressure to push the electrons. It pushes the electrons. All right.
Oh.
Yeah.
Yes,
So
sir.
that's basically it for this. Any other questions before we go? We'll talk more about it after lunch. All right, so you will take a hour break. All right, another question?
Yes. On a battery, there's a top part with a little bump, and then the bottom part, which is completely flat.
All right.
What are those two sides?
All right, so if you realize on your, if you know your AA battery, right, you would know that there's a, I think this is the positive end, and there's a negative end. All right, so electrons will flow essentially. They usually flow based on the orientation of your of the battery. So they usually go from the negative end around to the positive end. So this section with the bump here, if you look on the battery in real life, if you take a battery out of probably the remote or so, you will see the positive side. All right. Any more questions?
Yes, sir. What does the 8.16V represent?
Go again.
What does the 8.16V represent?
That is the
Amount of
value.
voltage?
Yeah, that's the value of our voltage. So if we increase the voltage over here, right, that would increase the actual value, the value of the voltage, and therefore the pressure that the battery puts out on to cause the electric flow of charge.
What happens if there is too much voltage?
That's a good question, right? If there's too much voltage, that can cause damage of the equipment. That can also cause, if you realize that when you increase the voltage, what happens to the temperature?
It rises.
Right, so it gets hotter, and eventually that can cause our systems to burn, right? So we have to have mechanisms in our systems that would cause that if the temperature gets too high. That's why when you have power outages, there could be a system that is pulling too much power, right? And the voltage is just too high, and to protect the system, they just shut it down and let the system resets. That's why you have power outages. Or it could be that the voltage is too high going out, and their equipments are damaged. The wire gets too hot and eventually burns, and that causes that could cause persons to get damaged, hurt, right? So you want to shut down the entire system, and then light goes away, right? So these are some simple things, right? Any more questions before we go?
No, sir.
All right, so we'll pause here and we'll go for lunch. All right. All the best.
Yes, sir.